In a 480-volt 3-phase 3-wire feeder consisting of two parallel 3/0 conductors per phase, each 100 feet long and carrying 200 amps per phase, we analyze a scenario where one of the phase conductors is cut. The question is whether cutting one of the parallel conductors would produce a huge arc, or any arc at all. The answer is no, a huge arc will not be produced in this case. Although 100 amps is flowing through the conductor, all of the return current is in the other parallel conductor. Therefore, on the conductor that is being cut, the magnetic field immediately surrounding the conductor is essentially zero. Remember that if the magnetic field is zero, there can be no inductance, and if there is no inductance, there is no collapsing magnetic field when the current is interrupted. Next, we analyze whether the choppers used to cut the cable would be damaged. The answer is no, the chopper should not be damaged, because there is not going to be a large arc as you would expect when cutting a single energized conductor. Again, because there is no magnetic field immediately surrounding the conductor that is cut, there is no induced voltage, no spark, and no arc. Now, considering the scenario where the individual removes their gloves after cutting the cable and touches both ends of the cut cable simultaneously while remaining ungrounded, the question is whether they would get shocked. The answer is no, they will not get shocked. Because the individual is not grounded, there is no completed path for current to flow. The person is floating at 480 volts. They are not getting shocked because they do not have a different potential than the conductors that they are touching. However, it is important to note that if the person grounds themselves to earth, or grabs both conductors with one hand, then they will be shocked. But as long as they stay isolated from ground and only touches one conductor at a time, they will be safe. Firstly, it is crucial to understand the principles of current flow in parallel conductors. In a parallel conductor system, the current divides between the conductors based on their impedance. Ideally, if the conductors are identical in length, material, and insulation, the current will split evenly. Secondly, the concept of a magnetic field surrounding a conductor carrying current is fundamental. Any conductor with current flowing through it generates a magnetic field around it. The strength and direction of this field are directly related to the magnitude and direction of the current. Thirdly, inductance is a property of a circuit element that opposes changes in current. When the current changes, the magnetic field also changes, inducing a voltage that opposes the change in current. Fourthly, when a conductor is cut, the current is interrupted, and the magnetic field collapses. If there is significant inductance, this collapse can induce a large voltage, leading to an arc. Fifthly, in the case of parallel conductors, the magnetic fields of the conductors tend to cancel each other out if the current is flowing in opposite directions in close proximity. This is why the magnetic field is minimal around the conductor being cut, as the return current is flowing in the adjacent parallel conductor. Sixthly, the absence of a significant magnetic field and inductance means that there is no substantial voltage induced when the conductor is cut, preventing a large arc. Seventhly, the concept of grounding is essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to operate and clear the fault. Eighthly, if a person is not grounded, they are effectively floating at the potential of whatever they are touching. In the scenario described, the person is floating at 480 volts, but there is no current flow because there is no return path to the source. Ninthly, if the person were to ground themselves, they would create a path for current to flow, and they would experience an electric shock. The severity of the shock would depend on the voltage, the impedance of the path, and the duration of the contact. Tenthly, it is important to emphasize that working on energized circuits is extremely dangerous and should only be performed by qualified individuals with the proper training and equipment. Lockout-tagout procedures should always be followed to energize circuits before working on them. In general, electrical safety relies on understanding several key concepts. These include voltage, current, resistance, impedance, grounding, insulation, and overcurrent protection. Voltage is the electrical potential difference between 2 points. Current is the flow of electrical charge. Resistance is the opposition to current flow. Impedance is the total opposition to current flow, including resistance and reactance. Grounding provides a low impedance path for fault current to flow back to the source. Insulation prevents current from flowing where it is not intended to flow. Overcurrent protection devices, such as fuses and circuit breakers, protect circuits from excessive current. When working with electricity, it is essential to follow all safety procedures and use appropriate personal protective equipment, such as insulated gloves, safety glasses, and arc-rated clothing. It is also important to be aware of the potential hazards and to take steps to mitigate them. These steps include energizing circuits, using lockout-tagout procedures, and maintaining a safe working distance from energized equipment. Furthermore, a comprehensive understanding of the National Electrical Code, or NEC, is paramount for anyone involved in electrical work. The NEC provides detailed guidelines for the safe installation and maintenance of electrical systems. Compliance with the NEC is essential for protecting people and property from electrical hazards. Specifically, Article 310 of the NEC covers conductors for general wiring. It specifies the allowable ampacities of conductors based on their size, insulation type, and installation conditions. When sizing conductors for parallel installations, it is essential to consider the requirements of NEC Section 310.10. This section requires that parallel conductors be the same length, conductor material, circular mil area, insulation type, and be terminated in the same manner. Additionally, the overcurrent protection device must be sized to protect the smallest conductor in the parallel set. Article 250 of the NEC covers grounding and bonding. It specifies the requirements for grounding electrical systems to ensure that fault current can flow back to the source, allowing overcurrent protection devices to operate and clear the fault. Proper grounding and bonding are essential for electrical safety. Article 110 of the NEC covers general requirements for electrical installations. It includes requirements for working space around electrical equipment, guarding of live parts, and identification of equipment. Compliance with Article 110 is essential for ensuring a safe working environment. Additionally, understanding the concepts of short-circuit current and arc flash hazard is crucial for electrical safety. A short circuit is an unintentional connection between two or more conductors, resulting in a large flow of current. An arc flash is a dangerous release of energy that can occur during a short circuit, creating intense heat, pressure, and light. Arc flash hazards can be mitigated by using appropriate overcurrent protection devices, arc-resistant equipment, and personal protective equipment. Furthermore, it is important to be aware of the potential for static electricity to build up and discharge, especially in dry environments. Static electricity can ignite flammable materials and damage sensitive electronic equipment. Static electricity can be controlled by using grounding straps, humidifiers, and anti-static sprays. In addition to the NEC, other standards and regulations may apply to electrical work depending on the location and type of installation. These standards and regulations may include those from the Occupational Safety and Health Administration, or OSHA, the National Fire Protection Association, or NFPA, and local jurisdictions. It is essential to be familiar with all applicable standards and regulations and to comply with them. Ultimately, electrical safety is a shared responsibility. Everyone who works with electricity must be aware of the potential hazards and take steps to mitigate them. By following safety procedures, using appropriate personal protective equipment, and complying with all applicable standards and regulations, we can create a safe working environment and prevent electrical accidents. To further elaborate, consider the specific scenario of cutting a conductor in an environment with high humidity. High humidity can increase the risk of electrical shock because moisture reduces the resistance of the skin, making it easier for current to flow through the body. Therefore, it is essential to take extra precautions when working with electricity in humid environments, such as wearing insulated gloves and ensuring that all equipment is properly grounded. Another factor to consider is the type of insulation on the conductors. Different types of insulation have different voltage ratings and different resistance to environmental factors such as heat, moisture, and chemicals. It is essential to select the appropriate type of insulation for the specific application and to ensure that the insulation is in good condition. Damaged insulation can create a path for current to flow, leading to electrical shock or equipment failure. Furthermore, the age of the electrical system could affect its safety. Over time, electrical components can deteriorate due to corrosion, vibration, and other factors. Regular inspections and maintenance are essential for identifying and addressing potential problems before they lead to accidents. These inspections should include checking for loose connections, damaged insulation, and corroded components. In addition to the technical aspects of electrical safety, it is also important to consider human factors. Fatigue, stress, and distractions can all increase the risk of electrical accidents. It is essential to be well rested, focused, and aware of your surroundings when working with electricity. If you are feeling tired or distracted, it is best to postpone the work until you are in a better state of mind. Moreover, communication is crucial for electrical safety. Before starting any work on an electrical system, it is essential to communicate with all affected personnel to ensure that they are aware of the potential hazards and the steps being taken to mitigate them. This communication should include a briefing on the scope of the work, the potential hazards, and the safety procedures that will be followed. Furthermore, it is important to have a clear and well-defined emergency response plan in case of an accident. This plan should include procedures for contacting emergency services, providing first aid, and shutting down the electrical system. Everyone who works with electricity should be familiar with the emergency response plan and know their role in it. Moreover, the selection and use of appropriate tools and equipment are essential for electrical safety. All tools and equipment should be in good condition and properly rated for the voltage and current levels involved. Insulated tools should be used when working on energized circuits to prevent electrical shock. Additionally, it is important to use appropriate personal protective equipment such as insulated gloves, safety glasses, and arc-rated clothing. This equipment should be properly fitted and maintained to ensure that it provides adequate protection. Furthermore, training is essential for electrical safety. All personnel who work with electricity should receive comprehensive training on the potential hazards, safety procedures, and applicable standards and regulations. This training should be regularly updated to reflect changes in technology and safety practices. The training should also cover the proper use of tools and equipment, including personal protective equipment.